This unit is all about the concentration of solutions. By definition, a solution is a mixture. In the case of a solution, it's a homogeneous mixture, meaning everything is dispersed evenly throughout. A solution has two components: the solute, the substance that is dissolved into the solution, and the solvent, the substance doing the dissolving. Think of a batch of Kool-Aid, where the water is your solvent, the Kool-Aid mix and the sugar are your solute. In this unit and the next, we will refer to two types of solutions: electrolytes, those that conduct electricity, and non-electrolytes, those that do not conduct electricity. Commonly, electrolytes are salt solutions. Non-electrolyte solutions are typically sugar solutions. Listed here are some other examples of each. Like the demo that I did in class, we can use a setup to demonstrate electrolyte solutions that connect the electric charge between two electrodes to a light bulb. If the light bulb comes on, you have an electrolyte solution. I demonstrated salt water in class. If the bulb does not come on, that solution is a non-electrolyte. In the class demonstration, that was the pure water. I could also have mixed up maybe some Kool-Aid. That would have been a non-electrolyte as well. When dissolving solute into a solvent, there are ways of getting it to dissolve faster. Increasing the surface area is one way. That can be accomplished by cutting it into smaller pieces, crushing the solute if they're crystals, stirring the solution to increase the interaction between solute and solvent, and likewise shaking. Increasing temperature can also cause something to dissolve more quickly because the added energy energizes those interactions between the solute and solvent particles. We demonstrated that one time in class with some green food coloring and hot and cold water. In the hot water, the green food coloring dispersed quickly. In the cold water, it did not. It's the same when mixing a solution. When a solution is concentrated, it means the ratio between solute and solvent is high. When a solution is dilute, that means the ratio between solute and solvent is low. Think of concentrated as being a strong concentration. Think of dilute as being weak. We use these terms, unsaturated, to mean there's less solute than a saturated solution, saturated to be the maximum possible amount of solute in the solution that will dissolve, and then supersaturated, where there's actually more solute than is possible. This is accomplished by heating the solvent, just like when we made the chemistry ornaments and we used a warm solution of borax. Then as it cools, the crystals will begin to form. The rate of the solubility for each substance can be graphed. On this particular graph, referred to as a solubility curve, it shows the solubility of a certain number of grams of salt in 100 grams of water versus the temperature. You'll notice that each of these substances, sodium nitrate, calcium chloride, lead 2 nitrate, for example, all increase with the increase of temperature. Every now and then you'll find a substance such as the selenium sulfate down bottom that actually decreases in solubility as temperature increases. In order to use this graph effectively, you have to recognize that the actual line is the point of saturation at each temperature. Find potassium chromate It's a purple line in the middle. Find 50 degrees Celsius. Notice that potassium chromate at 50 degrees Celsius corresponds with the intersection on the left of 30 on solubility. So at 50 degrees, potassium chromate is saturated with 30 grams. If we have more grams than 30, that would be a supersaturated solution at 50 degrees. If it was less than 30 grams at 50 degrees, that's below the line, and that is called unsaturated. Here's a sample problem. A solution containing 75 grams of lead-2 nitrate and 100 grams of water is saturated at one temperature. Now the 100 grams of water corresponds with the y-axis to tell you what the solvent is for the solution. It does not affect the reading that you're trying to do of this graph. This graph is about grams of solute per temperature. Notice that the lead-2 nitrate is circled at the 40 degree mark because that corresponds on the left with a quantity of solute of 75 grams. So the answer is 40 degrees Celsius. As already mentioned, solubility can be affected by increasing the temperature, increasing the surface area. With gases, sometimes decreasing the temperature is effective, and then also changing the pressure will affect the solubility of gases. The effect of solid solutes and gaseous solutes are different from each other. Solids tend to dissolve best when heated, stirred, ground into smaller particles. Gases, however, tend to dissolve best when the solution is cold and pressure is high. The definition of the word concentration means the measure of the amount of solute in a given amount of solvent, or solution. The picture demonstrates a typical chemical bottle in the lab. This hydrochloric acid solution is a 6 molar concentration, meaning that for every liter of solution, there are 6 moles of solute. This is a concentrated solution. There are two ways to describe the concentration of a solution: by its molarity, based on volume, or its molality, based on its mass. Here are two excerpts from your textbook with the definitions of molarity and molality. Take a moment to read these. Of course, you'll be responsible for knowing the definitions of each. When calculating molarity, the amount of solute divided by the volume of solution in liters will give you the molar concentration. Molality is computed by taking moles of solute per mass of solvent given in kilograms. If I were a student in the lab needing to make a molar solution, I would need to remember that it's moles per liter. In this sample, it says determine the amount of solute needed to make a 0.5 molar sodium chloride solution. That would be rather dilute, by the way. It says describe how to make the solution. Well, first, I need to figure out how many grams of solute would be required to make a 0.5 molar. I know that a 1 molar would be equivalent to the molar mass of 58.44 grams. But half mole of solution would be half of that, 29.22 grams of the solute in NaCl. It says to place that measured amount, the 29.22 grams of NaCl, into a volumetric flask. Dissolve completely in a small amount of the solvent, usually water. Shake or heat if needed. Then increase the solvent volume to exactly 1 liter. There's a mark on the volumetric flask for exactly 1 liter. When mixing these two types of concentrations, you wind up with a different yield. With molar solutions, you get exactly 1 liter of solution, because that's how you make it. When making a molar solution, you start with a kilogram of solvent, which is the same thing as a liter. Then you add the salt, that increases the volume. So you actually end up with a little bit more than 1 liter of solution. In this question, they are discussing making one of these molal solutions based on the mass. Similarly, it's asking for a 0.5 concentration. This time it's 0.5 molal NaCl. You have to use the molar mass to calculate the mass of the solute, but the directions are a little more simple. You just mix exactly 1 kilogram or 1 liter of solvent, add in the measured amount of solute. It does not have to be in a volumetric flask, and you just stir it together, and that's it. This excerpt from the book demonstrates how to make a proper molar solution. And this excerpt in the book demonstrates how to make a proper molal solution. In our further studies in chemistry, we will use molal solutions at times for our calculations, and molar solutions at times for other calculations, like acids and bases. If you need, go back and watch this video again. The concepts, the definitions will all be included on your next assessment.